Okay, it's just after 4. We're going to get started. We're going to do a little bit of sort of some stuff before the first question, which I know is a little unusual. So last class, we ended off looking at the textbook problem on the gambler's problem. And we were here in chapter 4, which the textbook calls dynamic programming, which just means using what you know to like figure out other stuff. And we were specifically doing this value iteration algorithm. And in fact, your homework that you just submitted was all of them could be done with value iteration by setting up the R's and the terminal V's correctly. So there's these ongoing rewards that you can get every time you step on something. There's these terminal rewards, and together you can all solve all sorts of things. This is the Bellman equation, and solving it this way is called the value iteration algorithm. And here it is written out as an equation. So in iteration k plus 1, we set the value of state S to be the best possible thing we can get of R plus gamma times what it was in the previous iteration, averaged over the probabilities. So the sum of p times a thing is doing the effect of the average value. In your code, this would be some kind of matrix. And very often, actually, we don't implement it as a matrix. We say like, oh, the state plus 1, state minus 1, that kind of thing. Okay, and we had a few examples. Okay, here's another way to write it as an algorithm. Oh, I clicked on something. Okay, and we got to this problem, which was the gambler's problem. So the gambler's problem is some kind of generalization of the drunkard's walk. So you start at some amount of money, and the game ends when you get to the maximum amount of money or to 0, just like in the drunkard's walk. But the difference is the step size is not necessarily 1, and that is because the gambler can bet any amount of money they want. So they have a goal of $100, and let's say they start at $50. So they can bet $1, and then they'd go to $49 or $50. They can bet $10, and then they would go to $60 or $40, and they can bet any amount they want. And the question is, what is the best amount to bet? That's what we're trying to find out. And the reason this problem is a little bit trickier than the other ones we've looked at is because the number of actions is, 1, a lot bigger than 2. So there are many possible actions you could take at any state. And 2, the actions depend on what state you're in. If you're in state 10, you're not allowed to bet $20. So that makes it a little trickier. So that was the gambler's problem, and that is where we ended off last class. So that's where we're going to pick up today. I sometimes call it How to Gamble If You Must, which is also the name of a famous book in probability where they worked out the solution to this problem with pen and paper. We're going to work it out with a computer. And here's the little gambler at $50 who is deciding how big of a step he wants to take. Any questions or comments about the gambler's problem so far? What is it asking? How is it set up? Okay, so I solved this 2 different ways, and both of them are really the same thing. I just solved it with for loops. So with for loops in the code and without for loops. So that's what I'm going to show you sort of quickly without for loops. And in either case, we're always iterating the Bellman equation. So we have the two big tenets of the Bellman equation that we already saw, and one of them says V of S is the maximum over the allowed actions. So we got to somehow enforce the allowed actions. Then you have the reward now, on average, plus gamma times the reward later. And the reward later, in this case, you can write it like this. It is P times V of S plus A plus 1 minus P times V of S minus A. So maybe this is the secret sauce to this problem is this line over here. And that's another way to say that is if you bet an amount A and you apply that to the value function V at state S, that is a P chance of moving up by A and a 1 minus P chance of moving down by A. And so you can write it like that. So we don't actually write out the full matrix. We just use the action of the matrix on the vector V of adding or subtracting A. Yeah?
Do the rewards in this game not depend on the action?
Yeah, this is a great point. Let me put the rewards here. Let me do this. So it should be SA. Let's fill that in as well. So over here, maybe I should have written it with an M, and then I should have said this is what M is. What are the rewards in this game? R of SA equals what? Does anyone want to tell me what the rewards are for this one? So you're at state S, you take action A, how much reward do you get? More specifically, this is the average reward, right? This is the reward you get on average when you're at state S and you take action A. What would that be in this case? Should we go back to the picture? Maybe I should open up the PDF, because the PDF has the full things. Okay. Let's see. A gambler has the opportunity to make bets on outcomes of a sequence of coin flips. If the coin comes up heads, he wins as many dollars as he had staked. If it's tails, he loses his stake. The game ends when the gambler wins by reaching his goal of $100 or losing by running out of money. So what are the rewards? Yeah.
It says it there when you transition to the final state.
Yes, where does it say that? Very good.
Reward is 0 on all transitions,
Yeah, there we go. Look, the reward is 0 on all transitions except when you reach the goal and then you get +1. So this is an important thing to realize about this problem, is that there are no rewards except for at the very end. So the way I have been saying this in this course is you can think of dividing up rewards into 2 different types. There's ongoing rewards. Those really go in the R vector, and they're like every time you're in state S and you take action A, you get this reward R. And then a separate type that you can think of is what are the terminal rewards at the terminal states. So in this problem, there are no rewards at all on the way, so the reward is 0. And this is no ongoing rewards. Ongoing rewards. If you wanted, you could phrase the problem in a different way, and you could think of a reward as like, oh, if you get to the end, then you get an ongoing reward. But I think it's easier to think of it as having terminal rewards, which are v of 0 equals 0 and v of n equals 1. And these are what I call terminal rewards. Terminal rewards. Okay. And the project that you guys just did, or the assignment, was all about you had 3 separate problems with different mixes of ongoing rewards or terminal rewards, depending on what you wanted to solve. So I'll probably post some solutions for that at some point. But all 3 parts of assignment 2, parts B, C, and D, they were all just, if you set up the R's in the right way and the V finals in the right way, then you can crank out the right answer however you go. So v of 0 equals 0, v of n equals 1, and there's no R's at all in the middle. One other thing is gamma equals 1. So there's the discount factor is just 1 here. There's no future discounting at all. So the reward you get now is just the sum of the rewards in the future. Okay, so that's the equation for V. And then there's one other thing you got to do, which is the equation for Q, which says that Q of SA, so you take action A, and then you follow V forever after that. So this is, again, this is this thing over here. So it's a P of V of S plus A plus 1 minus P times V of S minus A. So that's the Q, and then the V is the maximum of the Q's, and so on and so on. Okay, so these are the equations. To do it in the computer with value iteration, you write a big for loop, and you apply these over and over again. I'm going to show you how to implement it 2 ways, with or without for loops, and making sure that we deal with this little detail, that the A of S, the actions that are allowed at state S, are a little different. Any questions about the theory before we move to the code? Okay, maybe before we move to the code, let me motivate you to pay attention, which is I have posted assignment 3. And assignment 3 has 2 problems, one of which is the gambler's problem. So let me see if I can find this. Okay. Here is assignment 3, which will be due a whole week after reading week. So I guess if you don't want to start it now, you can wait till after reading week. There's 2 problems. One of them is finding the optimal strategy in EZ21. EZ21 is like a variant of blackjack. This is very similar to what we did with the pig problem. You can either hit or stay at any given time. Yeah, that's what you have to do. And the other problem is the optimal gambler strategy with a fixed number of rounds and a savings account. So it's like the problem we're doing now, but it has 2 little twists. One is instead of gambling forever, this gambler, he gambles for 5 rounds or something. and there's also this savings account. And I'll give you a hint. The savings account means that sometimes there are rewards. So in the problem we're doing now, the rewards are always, these ongoing rewards are always 0. But with the savings account, they're sometimes non-zero. So that's the homework problem that you're going to be doing. And it is some kind of like more complicated version of this thing. I also gave a hint on the course link with some nice plots of what your output is supposed to look like. So that'll be assignment 3. Okay, so yeah, let me show you the 2 solutions now. One with for loops and one without for loops. Unless someone has a question. No? Okay. Let's bring in this. So here it is with for loops, which I think is the sort of easier one to start out writing. So if you're sort of confused and don't know what to do, then I would recommend you try it with for loops to start. And let's see if we can make this bigger. So this is the output to the program, which is all these different iterations. Let me see if I can zoom out a bit. Iteration 42, start at iteration 0. So at this is the output to the program, which has the value for a v in red, and it has the optimal bet size it found. So the v function is the maximum of the q functions, and the optimal bet size is the argmax, which bet size gives you the maximum. And it starts out as all ones, and the v function is all zeros to start except for 1 at 100. But then as you do iterations, it starts to go up. And here I put in p equals 0.3. So after one iteration, the value function says, oh, if we bet all our money at more than 50 steps, then we have a 0.3 chance of winning the game. Because if we win our first bet, then we win. But of course, the value function is actually a little bit larger than that, because you don't have to win right away. You could lose your first bet and then still win. So it starts to look like this. And so if you're between 80 and 100, actually it thinks your chance of winning is quite high, is like 0.5, because you could either win now, that's 30% of the time, or you could lose now and then win later. And that's 70% chance times 30% chance, that's like a 20% chance. So altogether, your chance of winning is like 50%, very good. And of course, this iteration continues, and you iterate, and you get this beautiful fractal-like curve over here at the end with what is your chance of winning from any starting point. And after a few iterations, it figures out that your optimal bet is always just bet all your money. So go all in every hand and hope to win. That's your best bet when you have a 30% chance of winning. You want to just bet all your money, and you get this weird curve. So that's the answer. I'll show you the code in a second. Questions or comments about the setup or what the code is doing? Again, your homework problem is going to be to basically recreate this for a slightly harder problem. Yeah, there's a question over here, or no? Okay. So let's look at the code. And the code, again, very similar to what you did in assignment 2 and before, except for now you have to also deal with the policy, right? So in your question, the policy was fixed and given to you. In this one, the policy is sort of computed on the fly. So n and p win, those are the parameters in the problem. If this was going to be a homework problem, those would be the inputs to your function. And then I got v and q. V is the value function, just like it always has been. The thing that is annoying and new is that the q function really is a q function. So it's q of sa, and it inputs the state and the action. Up until now, we did a simple case where it was like q roll or q stop, and there were 2 different q functions. But now it really is like the q function like it is written in the math with q of s comma a. These are my hard-coded terminal states, v of 0 and v of n. And this is my policy, which I figure out by doing the argmax of the q. You'll see that in a second. And occasionally there's tiebreakers where the q function is like equal to itself, so that's what this q tiebreaks is going to be. Okay, then I do iterations. This is the iteration loop over here, where I'm going to do the value iteration algorithm over and over again. And here is the first little bit with a for loop. So what I do is I set v of s to be the maximum of q of s comma a. So that's exactly the line of the line over here. So the rewards are 0, gamma is 1. So it's the maximum of the q function. This thing over here is the q function. Very nice. Why is it slightly annoying? Because there's all these little details. Where did my thing go? Let's see if I can find it. Okay. So the thing that's slightly annoying is that you can't bet any amount of money. You have to bet an amount of money between 1 and what I call a max. And so when you're in state s, the maximum you can bet is the minimum of s or n minus s. You can't bet more than s, and you should never bet more than n minus s. That's like what you need to win on your next thing. So the maximum amount you can bet is this function, and I'm only doing the maximum up to here. Okay, so that's v of s. Very nice. And this calculates the policy. So based on this maximum, you would think the policy should just be the arg maximum. But then there's this annoying +1 over here. Does anyone know why you have to put in a +1? Why would there have to be a +1? Yeah.
Is it because Python zero indexes?
It is because Python is zero indexed in some sense. But I mean, it sort of has to do also with this stupid a max and this like 1 to a max thing. If I just did v was really the max, and then the policy wouldn't need a +1. So the fact that you need a +1 is because I had to do some weird shenanigans to q. And specifically, it's because I had to do this. So by feeding in the 1 to the a max +1, what is the 0th entry of this guy? The 0th entry of this guy is when a equals 1. So by starting at 1 here, I've sort of shifted everything by 1. So when you do the argmax, if the maximum happens at when this thing equals 1, it's going to output 0. So everything's shifted over by +1, which is quite annoying. So this is like a very bespoke like bug you can make over here. Very treacherous. Any questions or comments about that loop? Okay, and you'll notice it is a loop, a big loop over the number of states. So the bigger the number of states, the more you have to loop. You do all the states sort of separately. Okay, so that's the v is the maximum of the q's. And then next up, you need that the q is the given by the v's. Okay, and so again, you have to loop over all the s's. And again, you have a max is something that depends on s. And then now I have to do a second loop. So it's a loop in a loop. How annoying is that? And that's to calculate q of s comma a. And this is the formula p times v of s plus a plus 1 minus p times v of s minus a. And then I have to do the thing that we've done the whole course is make sure you don't have any overflows in your v's. So that's the equation from the notes over here in, let's say in green, this equation. Okay, so there we go. That's the code. Okay, this thing keeps coming up. I don't want this. Okay, I want the other one. Gambler's problem with for loops. Okay, great. Okay, great. And then the rest of it just plots, these little plots that we've already seen. But that works perfectly well. Any questions or comments about this code? So once again, it's important because you will be doing an assignment where you have to do this yourself. So, and you're going to be doing some variant on the gambler's problem. So you'll have something very similar with the gambler betting $A when he's at state S. Yeah.
Should we get a link to this?
Yes, I can give you a link. So far, up until now, I've been saying you could just watch the recording, and I've been kind of typing them out as we go. But if you guys if you want the link, I can give you the link. I to be honest, I feel like the link might confuse you more than just writing it down or watching the video, because you might copy and paste something that's not supposed to be there. But if you guys want, I'll give you the link. It's just someone has to email me and say, can I please have the link? Or post on Campus Wire. Okay. Questions about this one? Okay, so now what I want to show you is how would you do the same thing with no for loops. And once again, for your assignment, it's totally fine to do for loops. And especially if you're like new to Python, the other way, the array way, is like more complicated. So like the for loop way is sort of easier. We're gonna speed test compare them in a minute when they're done, and then you'll see why the other way is better. There's also, once you get the hang of it, the non-for loop way is also kind of like easier to read in some sense, and you get to avoid all these little bespoke little errors like this, and your code is shorter and sort of easier to read. But it's harder to set up, so pros and cons. So here is the same thing, the gambler's problem with arrays. Oh, I guess I got to rerun it. Okay. And so it's the exact same thing, except for the code does not have for loops in it. Or has one, it still has the iteration for loop, but not the other ones. Okay, so the beginning is the same, n the same number, p win 0.3, v and q. Here is where things start to get weird. So first, I make SA the NP indices of the Q array, basically. So remember, SA is np.indices of n plus 1. This lets me input S and A inside Q like this and change all the actions all at once. And the annoying thing about Q is that I want to access only the Qs where the action is a legal action. So I need to somehow tell the computer, do something different when the action is an illegal action versus when it's allowed, right? And that's because the states are only allowed in some, you're only allowed to bet certain things in certain areas. And that is what this legal state action array does. And what this does is it makes sure that it tells me which of the S and A combos are actually allowed. And the very first one is the most important one. A has to be, it can't be more than S or N minus S. So that's the most important one. And then the rest of them are like weird corner cases. So first of all, make sure you're betting at least $1. You can't bet $0. It's not allowed. And second of all, you can't bet if you're at 0 that if you're broke, you're broke. And if you're finished the game, you're also broke. You can't bet there either. So this is like, these are the places where the game is still going on. And they're all in one line. Whereas in the for loop solution, these lines all appeared, but they were distributed all over the place. So for example, in the for loop solution, you had this A max thing, which was doing the S and N minus S, but actually the 1 to N minus 1 was contained in here, in where the loops are happening. So it's kind of taking all the stuff that was distributed and putting it all on one line using this np.indices that we learned about last class. So that's an array of Booleans. And now you can set the Q of SA. There's this np.where function. And np.where really is the array version of an if statement. Let me write that down. np.where equals the array version of an if statement. And so what it does is it has the syntax of where this thing is true, it will do the first thing, and where this thing is false, it will do the second thing. So let's say np.where of a Boolean thing, it's like the true value and the false value. Okay, so this is like the syntax that if you want to learn how to do this array stuff, that's what you're going to have to use. And what this line is doing is it's setting Q of SA, it's setting to 0 wherever it's a legal thing, and it's setting it to -1 wherever it's an illegal thing. So if you try to do an illegal thing in this game, then instead of getting a reward between 0 and 1, you get a reward of -1. And by doing that, it makes sure that whenever I'm doing the maximum of this thing, I never ever accidentally pick an illegal action. So I think this is the trickiest part of this whole setup with arrays, is this kind of thing. Okay, the rest of it is pretty similar. You got V of 0 and V of N. I also set Q to the right things at the terminal states. So there we go. Any questions about the setup so far? Yeah.
So what does the ampersand mean?
Great question. Yes, this is an AND statement. So it's saying for it to be a legal state, this needs to be true, and this needs to be true, and this needs to be true, and so on.
In Python, can you just write the word and?
I don't think so. You can do and between two, like true trues and falses. You cannot do and between two arrays of trues and falses.
Oh, I see.
So this thing actually represents an array of shape n plus 1 by n plus 1. And so and is short for, yeah, this is a great question. So and is short for np.logical and. And similarly, like another one that we used was at. That at was short for np.matmul. So these little symbol commands, they're short for different specific NumPy commands. I think if you do AND is a specific Python command that is different. Yeah, great question. I think it'll specifically yell at you. It'll be like, the truth value of two arrays is undefined or something like that if you try to do it. Yeah. Right, exactly. Yeah, okay. Great question. Any other questions about the setup? Okay. All right. And then the for loop is the same kind of thing, so the same iterations. This for loop is unavoidable. You cannot, no matter how good you are at eliminating for loops, you will never be able to eliminate this for loop because the output of one iteration depends on what happened on the previous one. So like you can't do it in parallel. It really does depend on what's going on. You can't skip this one, so that's a good indication that you need this one. But the rest of the code, once it's set up, is quite nice. So first of all, V is just the maximum of the queue, and I tell it axis equals -1. That says do the maximum along the last axis. So do the maximum along the actions. And this replaces that entire for loop, right? So just this one line, V is the maximum of Q, it is skipping this entire thing. And you might think, oh yeah, well what about the Amax, right? That was baked into how I set up Q, right? So Q automatically has some -1s in the disallowed positions. So when I do the maximum, it will never return those -1s because it'll always look at the places where it's legal. So this whole for loop gets replaced by one line, which is this nice V. So if you set it up correctly, it can be very slick and very nice. Okay, questions about that one? The next thing is to find the policy. You do the argmax, and now it really works with no +1 or anything because I didn't have to do this like weird shifting or anything like that. So it is a lot more easy to read. You can also, if you're worried about tie breaks, there's some nice method to add some tie breaks, but let's not worry about that for now. So those are situations where there's more than one action that would lead to the same value, and then you can say like, oh, I want to pick the largest action or the smallest action or something. So I'll just leave this commented out for now. But there you go. There's the argmax and the maximum. That's the first loop. What about the second part? The second part, again, it is an if statement, right? Because I don't want to accidentally update the queues where there were illegal things. So that I do this kind of if statement. I say, if it's a legal, valid position, then replace it with the thing that we had before, which is P times V of S plus A, 1 minus P times V of S minus A. And if it's an illegal state, just leave it the way it was before. So this update is effectively applying an if statement and only updating the legal positions. It is not touching the illegal positions. It's leaving those at -1. So the whole thing from before gets replaced with 3 lines. Very slick, but again, harder to set up. But if you can learn how to do it, it is worth your time. And this is like when you do AI stuff, this is really important. Like getting these axes array things. This is the only way to make the computer fast enough to be useful. Okay, any questions or comments about that one? Okay, I guess the last thing we got to do is we got to race them against each other. Okay, so we got to see which one is faster. So let's run this one, and to make it fair, let me. Right now it's making a plot every iteration, but let me only plot 1 time. So it'll do one plot at the beginning and 1 plot at the end. Okay. Oh, it says NP is not defined. Yes, I can fix that. Okay. Okay, which one is this one? Is this the one this is the one with for loops? Okay, 1 second, not bad. Let's increase the n value so it takes a little bit longer so we can see. So this is n equals 1001, and how long will it take? Okay, so it's executing. So it plots it initially, it's gonna plot it at the end. And if we go to the variable explorer, it will also tell us what iteration we're on. So iteration equals 392. So 392. Out of how many iterations do I want to do? Oh, maybe that's A max. What? Okay, iteration 19. Okay, all right, 19 out of 100. That makes more sense. So we're doing 100, and it's slowly going up. And the reason it's so slow is because it has to do all these big loops over n, right? Every time. Let's wait till it goes up by 1.
I think as long as you're viewing it, it might not update the view.
It might not update the view. Yeah. Sometimes you can go over here and it'll show you. Did it finish? Okay, now we're on 40. Okay, great. There we go. Let's run the other one. So same thing, 1001. Same thing, and we got to plot only 1 time. Num iters, num plots equals 1. Please only plot it 1 time, and let's run it. And okay, is it going to complain that it doesn't know what NP is, or does it know? Did it figure that one out?
It does because you're right.
Okay, and this one I can go here. Oh, it's done. Okay, this one finished. Okay, so the array one finished in 10 seconds. How long did this one take? It's been 1 minute and 20, and it's still going. So it's at least 8 times as fast when you want to solve a problem with 1,000 states. Okay, what are we at? We're at 85 out of 100, so we're almost done. Okay, so what's the moral of the story? The loops are slow. It is much faster to do the array one if you can. It is tricky to set it up sometimes. Okay, there we go, it finished. How long did it take? It said 1 minute, I guess it said. Okay.
I think it was 1 minute 43 before reset.
Yeah, it's 1 minute 43, something like that. That makes sense. Okay, great. And the thing is, it gets worse and worse. So the bigger you make n, like if you make this 10,000 states, this one will take like 10x the time. Or will it take 10x the time? No, it'll take even longer than 10x the time because you have these like double loops that are like n squared. So it'll take like 100 times longer. Whereas the other one will still be sort of reasonable. So if you want to get sort of things done in reasonable amounts of time, you have to learn to do the arrays for the big speedups. Once again, for your assignments, it's okay to do it with the for loops. But if you can learn how to do this, it will significantly help you out in the final project. You'll be able to do things faster. You'll be sitting there less. Yeah.
So you mentioned that like you can convert it from a for loop to your array way if
Yeah.
the current iteration doesn't depend on the past iteration.
Right. Yes.
So is that like generally true that for any, or maybe not for
I think yeah. I don't think that's like a theorem, but it's like a heuristic. It's like if you're staring at a for loop and you're like, do I actually need one entry to the other, or are they like actually two separate things I could do? And if they're two separate things you could do, there's often these like array operations that will sort of tell the computer just do all of this stuff at the same time, and then like it'll send it to your computer and it'll like split it up in the CPU in a smart way so that it does it the right way. Yeah.
There's only one example that I know of that when I tried didn't work, which was if you try to do the thing that like an array accesses arrays in a vector and then some entries are repeated,
Uh-huh.
I'm pretty sure NumPy doesn't access them multiple times. So for that you're gonna need a for loop, otherwise you just access them once.
Okay, maybe ask me after class. I I'll have to look at a specific example.
I tried that in my assignment and that
Yes.
actually gave me problems for the transition matrix.
Yes, so very often it is hard to get it set up. I agree with that statement. I'll have to look at your specific situation. But when you can get it to work, this is like what you want to do. And like I said before, like the real reason this stuff is so important is to like it's used in AI systems. Like when you want to like train a batch, when they're like, we downloaded the internet and we ran all our stuff, they're not doing a for loop. They're doing it the array way. Okay. So it's a good skill. This is like a real life skill that will be useful for you if you can learn to use the arrays and these like axes operations. It will pay off in the future. And one good way to do this stuff is do the for loop version first and then see if you can upgrade it, right? And you know like what it's supposed to output, and you can try to fix it. Yeah. Were there any other questions or comments? Maybe over here. Okay. So that really is sort of it for value iteration, which leads us to the end of chapter 4. So chapter 4 was on dynamic programming, and you know there's some other stuff. This generalized policy iteration is kind of what we were talking about before, and is the value iteration that we're doing is a version of this. Okay, dynamic programming, blah blah blah. Summary, very nice, and then we're done the chapter. Okay, great. So we figured out how to do value iteration. Very nice algorithm that we've done. Hooray! We can solve some simple games. Oh, okay. Another important update. I also found this on the internet, which is a little thing where you get to play pig against a computer. So I'll include this as well. But you can like roll, and then you can roll and try to beat the computer. So it's actually pretty fun. Let's see. Okay, guys, I'm at 18. We'll roll one more time. All right, I'll stop there. And now the computer will go, and he's this little pig over here who's playing. Ah, he lost. Okay. Anyway, I'll include this in the course link. Okay, but now we are at one of the most important questions of the whole course. Which I will now open on Mathematize and have you guys think about. And I have to zoom out so I can get the present button. And the question is, will it load? Okay. The question is, why can't we do the value iteration algorithm for everything? So at the beginning of the course, I was like, we want to solve these games like chess and stuff. Why can't we just do value iteration? Seems to work pretty well. We can solve games like Pig. You got some tricky homework problems that are like blackjack, stuff like that. Why can't we just do it for everything? Like, why can't the course just be over now? Okay, I guess why can't the course just be over now is a different question than the question that we're trying to get. But like, what is it that we've done so far? Why can't we just do it always? So it's quite good for certain things, but it has some weaknesses, and I want you to think of what those weaknesses are. Okay, I'll let you guys think for like 2 minutes. It's a very like meta thinking type question, right? And I remember this thing doesn't like it when I do this. Okay. Great.
That's the thing I'm trying to get here. Once you start doing like the math thing, and you start having to add multiple times to the same state, using arrays to index the states doesn't work because Python only access each state once, even if it was multiple times. So yeah, I think you do need a for this case, but it'll
All right, there's like 30 seconds left. Put in your guesses for why we can't use value iteration, say, for chess. Okay, time is up. Let's see what you guys said. Why can't we use the value iteration algorithm for everything? All right. Ooh, this is a good word cloud. We got a couple twos. Two. We got actions in big letters. Many. Very nice. Okay, let's see what are the individual things. As we add more actions, our problems become much more complex and multidimensional. Value iteration may become too slow. Yes, this is one reason, and indeed you sort of saw it over here, right? Like as you start to loop, the sort of complexity of this algorithm depends on the number of states times the number of actions. And actually, even more, right over here, I was adding up. I was fortunate that in this game you can only move to 2 different states. Either you win or you lose. But you could imagine in principle you could move to n different states, and so I'd have to access n different things. So this is like an n cubed order amount of work you got to do over here. So as it gets bigger and bigger, it gets slower and slower, and you can try to speed things up by doing it like this. Fundamentally, you still got to do the operations. So this will only speed you up so much, and still bad. Okay, too complex state or action space, and you don't know where to place rewards. Yeah, so this is one thing that is potentially complicated. Is like knowing what the rewards are. Like if you have a situation where you really don't know what the rewards are, nothing we do in this course will help you. Fortunately, it's actually usually pretty easy to decide what the rewards are. So like you can decide like we won the game of chess or we lost the game of chess. That part is okay. Usually, like we kind of often know what is good or bad. Sometimes it's hard. It's like, is this AI generated poem? Is this a good poem or a bad poem? That's like a hard question. So usually the second thing isn't as big of a problem, but the complex state or action space, that is the problem. Yeah, too many actions or states. So again, because it's slow, state space is too big, very nice. Exponentially slower. I think it's polynomially slower, but yes, okay. Maybe things don't always converge. I guess that's also true. Usually the convergence is pretty good, so that can happen, but usually not the issue. Some games can't be reframed as a Markov chain. It turns out if you just add enough stuff in your state space, then you can basically make everything a Markov chain. So you might, a good example is like, imagine there's some game where it's not like Snakes and Ladders. In Snakes and Ladders, if you get to a square, it doesn't matter how you got there. Imagine there's some game where you get to a square and it matters every single square you visited along the way. Well, just take the set of all the squares you visited and call that the state. So the state can be as big as you want, and then everything is a Markov chain. Like everything in the universe is a Markov chain if you make the state space big enough. But then the problem will be that the state space is too big. So yes, some games can't be reframed as a Markov chain with a small state space is a true statement. Okay. Yeah, very nice. So I think you guys are figuring it out. Very large number of states. That is the real problem. So too many actions, too many states. Okay, yeah, very good. So this is fundamentally the issue, is that value iteration and the Bellman equation, we kind of wish we could do it for everything. So value iteration plus Bellman equation. This is like very nice classical mathematical stuff, and we get the right answer. When it converges, everything works great. It's true sometimes you have problems with convergence, but not very often in practice. But it only works on situations that are sort of small enough that we can fit everything in the computer. But can only fit in computer, only fit, I'll put fit in quotes. So fit could be fit in the memory of your computer, or it could be fit in the time budget that you have to compute in computer for small state spaces. And so everything we've done up until now, it's like the gold standard of what we want to always do, but unfortunately it doesn't work in real life problems like chess, or even simpler problems than chess. It will still not work. So this is what we want to get around. And we're going to have two sort of improvements that really are taking the value iteration and Bellman equation and just like improving them by doing like hacky stuff, okay? And like trying to make it work in situations where it wouldn't fit on our computer the classical way. So everything we're doing is still based on the value iteration and the Bellman equation. You should think of it as that's like what we want to do, but it doesn't fit on our computer. So we're finding like little tweaks so that it still kind of works, even though it doesn't like fit classically. And the two major tweaks are, there's sort of two different paths that we're going to sort of explore in parallel. And one path is called Monte Carlo simulations. Monte Carlo simulations. And in a Monte Carlo simulation, what you do is instead of sort of knowing the exact probabilities for everything, you find a way to learn just from samples. So it would be like if I didn't know the exact probabilities for the dice, and I just had a bunch of samples, then it would let me still learn. So this is learn from data slash samples. And this is a sort of it can be an effective way to explore the space of possibilities, even if the space is too big to fit in your computer. So you can imagine if someone was like, please write down all the chess games. You can't do that. There's no way you're going to be able to learn anything because you can't write down all the chess games. It's too big. It doesn't fit in your computer. But if I just say, give me 1,000,000 chess games generated like according to people playing, maybe I can learn something from those 1,000,000 chess games, even though they're sort of like random samples of what I would really want to do. And so this has an extra bonus, which this also works in situations where we don't know the rules. So this is like an extra bonus. Works when you don't know the rules. And a good example of this is working with robots. Like you can imagine the robot, we command it to put power on its wheels. We don't actually know the terrain. We don't have all the physics modeled of what the universe is doing. So the robot puts power on its wheels and it ends up somewhere, and we would like it to learn based on what happens. So this kind of idea of thinking of, you have some inputs, what comes out is going to be some random sample of reality, and we're trying to learn from those random samples. That's called Monte Carlo learning. So that's one thing we're going to do. Any questions about this Monte Carlo stuff? We're going to see some more of this later today. The other thing we're going to do is we're going to move away from arrays. So we're going to try to get parametrized functions over arrays. Parametrized functions instead of arrays. And at a functional level, what this is going to mean in your code, right now all of your code looks like this, v of s. That's what it looks like, v square bracket s. There's the state s. We look it up in our set of states we've stored, and we look at the value of v of s. Later in the course, we are going to do v of s like this with circle brackets. And so v is going to be a function. It's not going to input the state s. It's going to, or I should say, it's not going to look up the state s. Excuse me. From a table, it's going to input s as an input, and then it's going to do some sort of calculations on s and output something. And very often it will depend on parameters. So it'll have parameters, and it'll be a function instead of an array lookup. Array lookup. Okay, and I guess one cute thing that you can do at this point is you can put in verses, because then it says verses, 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 which is too good to pass up. Okay, so that's like what we're going to do. Why would that be helpful? Can anyone think of why would it be helpful to use functions instead of array lookups? Yeah.
Because you don't have to store the value function anywhere because the computer on the fly.
Yes. So this is one thing, is that maybe there's like billions and billions of states. It could potentially be cheaper to sort of, in terms of memory, to store it as a function. But that's definitely true. So that's one advantage, is like less memory potentially. But there's another big benefit by switching away from array lookups to functions. So these are pros. Yeah.
Is it something to do with you don't have to like pre-initialize the functions?
No, we're still going to have to initialize them, so that part will be the same, kind of either way. But I think you're onto the right kind of thing, which is like, what happens like the first time we reach a state? Right? Like, so we're learning, we're looking at the states. The very first time we see a state, what will happen in these two different universes? That will help you answer the second problem. Was there a hand up in the back? I'll let you guys think for a minute. I think it's a good thing to think about. Yeah, so let's look at a question, which is, what happens in the two setups the first time S is encountered? So that's what I want you to think about. So let's think of the array lookup, right? So suppose we're playing chess. S represents a state. We have initialized V. We're learning V over time by doing, like playing lots of games. We're like getting good at V. And then we reach some new chess position we've never seen before. Actually, this happens quite a lot. In basically every game of chess you play, after like 10 moves, you've reached a new chess position you've never seen before. What will V of square brackets S be in a new chess position we've never seen before? What will that be equal to? How will that tell us something about the state, if it's a good state or a bad state? Some people are shaking their heads. Yeah.
Will it be 0 since we've never seen it before?
Yeah, it'll just be whatever we initialized it to. So we've been initializing it to 0. And so basically, in this setup with an array lookup, when you reach a new state, if you've never seen it before, you're like, I don't know anything about this. All the stuff I've learned about chess, that was for other states, not this state. They got nothing to do with each other. On the other hand, if it's a function, then maybe we can learn something about the state S, even if we've never seen it before, by thinking of nearby states. Yeah? Yes, exactly. Yeah, it is related to rate of change. So, and this idea is called generalization. And so, like, the big idea is if S1 is approximately the same as S2, then V of array lookup S1 has nothing to do with V of S2. Right? If you're looking up an array and you have two states, no matter how close they are together, if they're different states, then they're just different array lookups. You get different numbers. On the other hand, V of S1 can be close to V of S2. And in particular, when things depend on parameters, so when they depend on parameters, the parameters are going to tell you which parts of the state like matter, which parts don't matter. How do the parts of the state combine to sort of give a final answer? And we can learn, if we see a lot of states of one kind, we can learn about states we've never seen before by just generalizing the pattern. So that's why it's called generalization. And the hope is that like you play a lot of games of chess and you're like, when the knights are like this, that's good for me. When the knights are like that, it's bad for me. Even if you've never seen a particular state before, you can say, I've seen other states that are like this one, not this one exactly, and that will really have a huge amount of mileage. So in large state spaces, this is like absolutely crucial to learning anything, because every state you see is like a brand new state. You really need to generalize from your past experiences, even though they're not exactly the same as what you're seeing now. That's like an absolutely crucial component of behaving in a large state space. So both of these two things combined together are what let all these methods work sort of in practical situations, because what we've learned so far is like the hardcore like math. It's all perfectly fine as long as it fits in your computer. So these two sort of quote tricks are what are going to let it work for larger and larger problems. Okay, any questions or comments about that? That's sort of the general, very general setup. Yeah.
So what does close mean? Like, does it mean like
Yes.
metric structure on this?
Yeah, so you could think of it as having a metric structure. What we're going to find out, like you're going to see that we're not going to impose like what does close mean. The computer will figure it out sort of automatically. So we're going to write these functions v theta of s, and over time it's going to like learn about the situations it was given, and if it's generalizing correctly, then it will automatically sort of do this situation. Well, you'll give it a state it's never seen before, but somehow it's still pretty accurate because it was generalized well from the stuff that it did before. So you can think of it in terms of a metric structure or in some particular way. It's gonna turn out that as long as you parameterize things in the right way, it should happen automatically. Fingers crossed, hopefully. Yeah. Great question. Okay, and we're gonna start with the Monte Carlo one. Why are we starting with the Monte Carlo one? The answer is because it's the next thing in the textbook. Okay, chapter 5, Monte Carlo. Okay, so what does Monte Carlo mean? So what is Monte Carlo? What was that? Yes. Okay. So very technically, it is a place. It is a place. It's like a casino in Monaco. But a Monte Carlo algorithm. What is a Monte Carlo algorithm? It is a randomized algorithm. A randomized algorithm. And it's to compute a non-random answer. Okay, which seems kind of bizarre. Like if you want a non-random answer, why don't you just like do it without randomness? But you'll see why we want to do this stuff. And the very first example I have for you guys is calculating the expected value of f of uv for some particular function f. And this is a great example. If you want to know the average of some function, that's some number, right? Like that there's some honest to God answer to this thing. But it turns out there's a very nice simple random algorithm for approximating this expected value. But before we kind of go into that algorithm, let me put up the function f, and you guys can tell me what the answer is going to be. So here is the function f. It's a very nice function. It has two inputs, x and y, and here is the function. It does 4, and then it does the indicator function that x squared plus y squared is less than 1. So remember these indicator functions, they are either 1 or 0 depending on the condition in the bracket. So sometimes this is a 1, sometimes it's a 0, then we multiply it by 4. And u and v are going to be uniform random variables. So they're between 0 and 1. Those are the continuous random variables with whose probability density function is always 1. These are like the most basic continuous random variables that we even do in our first year probability course. And they're independent, so there's two independent ones. What is the value of the expected value of f of uv? Please answer to 2 decimal places. So first you got to do it sort of theoretically, and then we'll do it on the computer with a Monte Carlo algorithm and see how it goes. Okay, I'll give you guys a minute to think. You might need to draw a picture of a square or something like that to try to figure this out. Okay, 20 seconds left to put in your guesses. If you have no idea, I guess put in 1, 2, 3, like 123. We'll see how many people got this one. And again, yeah, if you drew the right picture, it should be pretty straightforward. I guess it depends how your probability class was too. Okay. Let's pause it here and see what you guys had. Reveal counts. Okay, 6 people said 1, 2, 3. 4 people said 3.14. 1 person managed to type, 2 people managed to type in pi exactly. That's the correct answer. So I guess I said 3.14 was the correct answer, but pi also very good. So this thing is exactly pi. Why is it exactly pi? Let's draw a picture. So this thing is pi for the function f of xy, which is 4 times the indicator that x squared plus y squared is less than 1. And that's because if you draw this geometrically, we're picking a uniformly random point in the square. So u goes between 0 and 1. V goes between 0 and 1. So we're picking a point uniformly at random in the square, and our function is 4 over here on the inside of the circle, and it is 0 out here. So f equals 4 here. F equals 0 here. So what is it on average? Well, some fraction of the time it's equal to 4, some fraction of the time it's equal to 0. The expected value of f equals 4 times the probability that f of uv equals 4 plus 0 times the probability is equal to 0. And what is the probability that it's in this region? Well, that's the area of the circle. So it's the area, I'll say, of, what do you call it, a quarter circle? A quarter circle divided by the area of a square. Okay, and that's 4 times pi by 4 over 1. So the whole circle altogether is pi. This little quarter of a circle is pi by 4, and it perfectly cancels out the 4 to give pi. So this is a non-random number, pi, and we're going to calculate it by using a random method, or we're going to approximate it by using a random method. And in this situation, when the thing that you want to approximate is the expected value of something, there's a very simple randomized Monte Carlo algorithm you could do, which is called do the mean. Do the, and some people use this fancy word, empirical average. So pi is the true average of the function f. The empirical average, that means do it with a sample. And so that says that the expected value of f of uv is approximately just what you get by doing some number of samples. So we'll go to number of samples, and we will just add up a bunch of independent copies of f of un over vn, and then at the end I'll average them. So I'll do 1 over n samples. So that's called the empirical mean, and we know from statistics class that the empirical mean should get closer and closer to the true average, which is pi. So this is a Monte Carlo algorithm for estimating pi. That's what we're doing here. Monte Carlo estimate for pi. Okay, any questions or comments about the theory before we go to back to the code? Okay, let's go to the code and do it. Okay, and I have over here Monte Carlo. Okay, so here is my function f. Okay, here's my function f. And it's called my f. It doesn't even have any inputs because I randomized the x and the y inside. So I said, let x be a random uniform, let y be a random uniform. I guess I could have called them u and v, but I called them x. And then I did 4 times, and then I did in brackets, x squared plus y squared less than 1, and Python knows how to convert that to an indicator function. So very nice, there we go. That's my function f, and it's using np.random.rand, which is indeed one uniform random variable. Okay, is it going to yell at me that I have too many things open? Okay, you can also do a dice roll. We're going to stick with f for now. Okay, and we're doing the simplest possible thing. Let's do like 10,000 runs, and we just do a for loop. We add it up, and then at the end we divide by n. Okay, and what do we get? We got 3.153. Pretty good. 3.15. Pi equals 3.15. Not a bad algorithm. Okay, that is the simplest possible thing. We're going to improve it in a number of ways, but all of it is based on this simple thing and getting more and more complicated from there. Questions or comments so far? Okay, question for you. How big does n have to be? That's the next question. How many rolls? Imagine we're trying to estimate pi using this Monte Carlo method. How many rolls do we need to estimate it to an accuracy of 0.001? So we want to get 3.141, which is the next decimal of pi. And we want to get, it could be wrong after that. So 3.1417, that would be fine. I think the next decimal is supposed to be 2. And of course, our algorithm is not going to be perfect. It's not always going to work. But how many rolls do we need to get this level of accuracy. And I gave you some different options, so you can decide over there. Okay, let me let you think for 1 minute. If you had a good stats class, you will remember this kind of thing in sample size discussions.
It might be 100%. I put it.
All right, there's like 10 seconds left for the last couple people to pick what they think it's going to be. Okay, time's up. Let's see what people said. All right, 11 people are at 1 million, which maybe they knew already because I had it at 1 million before. But very good, 1 million. Does anyone have a nice explanation of why 1 million is like the right order of magnitude? Yeah.
I don't think it's a good explanation, but like the 10,000 was 3.1.
Uh-huh.
I assumed 100,000 would be 3.14, and then I assumed 1 million would be 3.1.
Wait, but then,
I don't know if it's right.
oh, I see. So you're saying when you multiply by 10,
I don't know.
you got, yeah, okay. This is the right, okay, here's like a follow-up question, I guess, which is like, how does number of samples compare to error size? Error size. And I guess what you're thinking is if you multiply the number of samples by 10, then the error size goes down by 10. Which is like, this is like one possibility, which is the error size is 1 over the number of samples. So if you multiply the number of samples by 10, then the error size goes down by 10. That would be nice. Yeah?
I'm pretty sure that's wrong because I'm assuming the difference scales with the estimate of the standard deviation or the standard error, which means it scales by the square root of it.
That's right. So this possibility is actually wrong. And if you had a good stats class, you would have discussed at length that the error size is not like 1 over n, but it is like 1 over the square root of n. So this is like the one lesson you should have learned in your stats class. It was probably disguised by a bunch of other stuff that was less important. Okay, the error size is 1 over the square root of the number of samples. In stats class, you would have written then the standard deviation of the sample mean. That's what you would have written down. And there's a bunch of different ways you can calculate it, but it's always 1 over the square root of the number of samples times the true sort of standard deviation. So you should say it's proportional to this little squiggle means it's proportional to. So this is like the one fact from stats class that will be extremely important. It only goes down like the square root. So when you multiply the number of samples by 10, you don't get 10 times the amount of accuracy. You get like 3 times the amount of accuracy. I guess you guys, it was a happy coincidence here. So what I was going for is that if you want an error size of 1 over 1,000, so if the error size is 1 over 1,000, aka 0.001, 1 over 10, 1 over 100, okay, then the number of samples has to be 1 over 1,000. You take 1 over that and you square it. So this has to be the square of 1 over the error size for this to work. Squared, again, proportional to, which in this case is 1 million, 10 to the 6. So if you want lots of accuracy, you got to do number of samples, and it grows like super linearly. It grows by the square. Okay, let's check this out in the code. Okay, so in our code, so there's 10,000 gave 3.153. So it's not only the first decimal is right, the second decimal is wrong. If we multiply it so if I multiply by 100, then you should get one more decimal. So let's add multiplying by 100. So I did 10,000, and then if I do 1 million, then we should get 1 extra decimal, 3.142. So we still don't actually have that last decimal digit. We're going to have to make it even bigger. If you multiply by 10, then we get 3 times the amount of accuracy. So right now the error is like 0.01. If I multiply the n by 10, the error size should go down by a factor of 3-ish, and we should get that last decimal. Let's see. Okay, also takes 10 times longer. Okay, might be here a while. Any questions or comments while the computer is adding up numbers? 10 million times. Okay, there we go, 3.142. I still didn't get it. Okay, we're getting close. So what is the first big improvement is anytime you're doing this kind of empirical averaging, you can always figure out how big the error is just by estimating the variance. And this thing is technically the central limit theorem. But what you can do is you can estimate the variance by adding up the square of the things. And when you estimate the variance, then you can create a upper and lower estimate. And this is the kind of thing you do in stats class. So this is like improvement number 1. Don't just estimate the mean, estimate the plus minus. Improvement number 1. Estimate a plus minus using standard deviations. Okay, so instead of saying the expected value of f is approximately the mean, the sample mean, 1 to n of f of ui vi, what you should do is you should tack on a plus minus, and you should say like plus minus 2 standard deviations, and you can calculate the standard deviation from the samples that you have. So the standard deviation of the samples. And that's what this little code does. And so instead of just having one number, now you have like a little region, and you're like, I'm pretty sure it's between this and this. And you kind of have a better sense of how accurate you are based on the samples you have. So this is a really major thing to be aware of. Anytime we're doing something with Monte Carlo, you will not get the right answer. You will get near the right answer, and you can sort of understand how far you are by calculating the standard deviation. So this is like absolutely crucial for thinking about these algorithms. And here is I did it in code. So I got the mean, I estimated the variance, and then I used the fact that the standard deviation is the square root of the variance, and you divide by n because we're doing it for the variance of the mean, not the variance of the samples. So this is all stuff from sort of stats class. If you run this, then you get, so I did, how many did I do here? I did 4 million, and then at the end, it tells me not just the answer, it tells me, I think the answer is 3.142, and I'm pretty sure the answer is between 3.144 and 3.140. So, like, the true answer is in that region. This is only right 95% of the time because I did there's 2 standard deviations. But now I have a sense of how accurate is this. I know it's like somewhere between these 2 things. Yeah. Was there a question over here?
No, sorry, I just did 2. So like.
Yes. Okay. This is a good point. So this is the standard deviation of one individual sample, or not the standard deviation. Rather, it's the variance of one individual sample. The nice thing about averaging many things is that the sample variance, like the variance of this estimate for the mean, is this thing divided by the square root of n. So
It's just so pretty to see the like.
yeah.
When 95, 96, when 96, like.
Yes. Okay. Yeah. So this thing to get the plus minus, you take this thing and you divide it by the square root of 4 million. So you divide it by 2,000, and that's why these things are pretty close. Yes.
In the total variance calculation, you're dividing
Right.
by n. Why not by n minus 1?
Oh, you could also divide by n minus. Yeah, this is like a different way of estimating it. Sure. Yeah. There's like different ways to do this.
Never mind, 'cause you're using the.
My way is the unbiased way. There's some other stats way which has like lower L2 error or something. You divide by n minus 1. Yeah, this is all stats lore. Yes.
I think information bias. It's just giving you.
Right. The way I'm doing it is unbiased, but is like less accurate than the biased way of doing it. Okay. That's the summary of the story. It won't make a big difference here because n is 4 million. So if you divide by 4 million or you divide by 3,999,999, almost the same. Okay. Great. Other questions or comments? Okay. So that's one improvement. Can anyone suggest another improvement? That was improvement number 1. There's a whole laundry list of improvements. Improvement number 2. we want to make it faster and better. What else could we do? Let me give a hint. What was I saying is a good way to improve your code earlier in the lecture? Yes?
Remove for loops.
Remove for loops. Yes. Okay, look.
Remove the summation.
Look at this. Look at this stupid for loop over here. I'm adding up numbers, and then I'm waiting till I add it up, and then I add up the next one. Why would you wait? Just do all the numbers at the same time, and then take the mean. So this is a big use vectors. So don't do one sample at a time. Do some big number. And so this is the code now for the vector f. It does not return one sample of the function f. It returns n samples in one big long vector. And this is already faster because the computer is better at simulating like 1,000,000 copies of something than simulating one thing 1,000,000 times. When it computes this, it's like optimized to do lots at the same time. This will be much faster than the other thing. So okay, let's see. How long did it take me to do? How long did it took me 5 seconds to do 4 million. How many can I do in 5 seconds if I do vectors? So here's let's do 4 million. Let's see how long that takes. So what you do is you just run it and you do np.mean. And the np.mean command is also smart. So when you do the sum, it doesn't just do them in order. It sends different batches of pieces of the vector to different CPUs on your computer, and it does like the average of the individual pieces, and then it combines them. So it's a lot faster than the regular thing. So how long did this take? Name error. Uh-oh. My vector f. Oh, you have to run. Yes, you have to define your functions or they don't work. Okay. So this took 102 milliseconds, not 5 seconds. Can I do 40 million? Will that work? Eventually, it'll yell at you and say, like, I'm out of memory. Okay, this took still less than a second. So 400 million. So this is approximately 100 times faster than the other way. So you can do 400 million in about the same amount of time that you can do 4 million in the other one. This is taking... Yes, but when you do percent time, I think it runs it more than once. Let me get rid of percent time. Okay. Let's let it run, and I think it tells you like best of so many loops. So it like reruns it a bunch of times. Anyway, it's faster. Okay, it crashed. This is the one thing you gotta watch out for. When you put things in memory, if you make a big vector of size 400 million, eventually the computer will go, I cannot write down 400 million numbers at once, and it will get mad at you. Okay, so eventually it will break. Usually what you wanna do is find the biggest possible number you can do. What was that? Yes, that's true. The gnomes that do all the work in the computer have two even numbers of fingers, so you should do a power of 2 for n, but it doesn't make a big difference. Some of the gnomes just take a nap when you do a non-power of 2. Yeah, that's true, technically. And you can ask the computer like how much memory do you have, how many numbers can I write down? But anyway, okay, that's speed up number 1. You can combine speed up number 1 and 2. Okay, now I regret running everything. You can combine speed up number 1 and 2 very simply. So you get the samples, you calculate the mean, you calculate the variance. Very nice. Then you can do the same thing with before. Okay, now it's run out of memory again. Okay, ran. Okay, here we go. So here it ran 1,000,000 samples, and it told me the mean, it told me the upper and the lower bound for my big thing with the array. Okay, that is one major speed up. There's one other one that is more subtle, and this is something called a online algorithm. This is called an online algorithm. An online algorithm means just calculate as you go. Calculate as you go. Okay, and I'll show you what this looks like. Actually, let me write it down in math. So this is before. This is after. So before we were doing a for loop for n in range capital N, and we were doing total plus equal sample. And then at the end, we would say total divided by n. That was the answer. So we were dividing by the sample size. And one of the annoying things about this is if for some reason the loop doesn't finish, or like you don't get to the capital N that you wanted, you just have the total, but you like lost track of how many n's you did. So is there a way you can have it so that you can stop at any moment and take a peek and see how good it's doing so far? And the way is this online algorithm. It's very simple. It's very cute. What you do is for n in range n, And what you do is you update the mean. And you say the mean, you plus equal the sample minus the mean. So you start the mean out at 0. And what this is doing is this is updating the mean. So if the sample is bigger than the mean, then the sample will sort of push the mean up. If the sample is less than the mean, then this is negative and it will subtract from it. And so what this is doing is at every given step, it is updating what is going on so that the mean is like being pushed towards or away from the sample. And there's only one thing you have to do to make this correct. So as written, I'm doing mean plus equals sample minus mean. And so what that will do is the mean will always just be equal to the latest sample. You just have to divide by n. So this is like the secret sauce, 1 over n. And if you do this correctly, at the end of this loop, mean will really be the mean. So this is like, I guess this could be an exercise. Check that. Okay, let's say prove. That's a fancy word. Prove that if, let's say mu before is the mean of, say, sample S1 up to Sn, then mu after equals mu before plus 1 over, I guess in my situations, n plus 1 times Sn plus 1 minus mu before is mu after is the mean of everyone after S1 Sn plus 1. So if you want to convert from the mean of the first n things to the mean of the first n plus 1 things, you can take the mean of the first n and do a small correction to it exactly by this rule. This rule is this online algorithm. It turns out we use it a ton. So it's important to understand. And we do all sorts of loosey-goosey stuff, like we replace this 1 over n with any function that we want, and we do all sorts of crazy things. This is the online algorithm that calculates the mean as you go. You can stop the dice anywhere you want, and you'll always have the mean. So here is an example. So the nice thing is in this for loop, I can hit stop at any moment. So I can be running it, I hit stop, and even when I stop it, the estimated mean is always like a valid estimate, even if you stop it. Okay, I guess I should make even more, but that's the online algorithm. Okay, and you can do fancy things that give you the online algorithm for the mean and the variance. Turns out that's like less used, but this one, super important. You'll see why as we go later in the course. Okay, any questions or comments? Okay, in the last 1 minute of class, on Thursday is simultaneously two things. It is the last day before reading week, and it is also